Hello everyone, this is chapter 8.5, which is random variables, probability distributions, and the expected value. So, of course, we're only going to be talking about these three themes in this section. It's kind of a lot, but each of these topics are kind of, well, they're each based on the previous one, so it's kind of like a ladder, I guess you'd say. So we need one to talk about the next topic. For random variables, all a random variable is a numerical association between outcomes of an event. So this example here, tossing a coin 3 times is our sample space, so that's kind of the experiment we're conducting, I guess you could say. And the outcomes of that are the following. So here are the outcomes of our sample space. So remember that when you toss a coin 3 times, there's a total of, 8 possibilities, because with each toss there's 2, and since we're doing 3 times 2 to the third is 8. And what they are, let me leave space for them, 1, 2, 3, 4, 5, 6, 7, 8. So either you get heads for all of them, or 2 heads then a tails, or heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails. Do that again. Or tails, tails, heads, or all tails. So you can kind of take a look at how I constructed this basically. So I'm basically switching the last one to heads, tails, heads, tails, heads, tails. The second one is heads, heads, tails, tails, heads, heads, tails, tails. And the third one here is heads, 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 or tails, 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 tails. So these are the outcomes for our events. These are the total possibilities of the experiment. Now, x, in this case, is assigned to be the number of heads. So this will be a random variable. So what x is going to represent is a number that corresponds to each of these events. And in this case, this is the specific assignment that we're looking at. Now, depending on the problem, you'll actually see what the specific assignment is, and that'll be your random variable, of course. So here, how many heads are there in this outcome? Well, there are 3. Here there are 2, there are 2, here there's 1. So I'm just counting the amount of h's for each one. 2, 1, and I guess 1, and then 0. So in fact, x is literally just the set 0, 1, 2, and 3. Now you'll notice that some are more likely than others. In fact, 3 and 0 only occur once each. 2 and 1 occur 3 times each. So actually 1 and 2 have more of a weight associated with them. And these weights are essentially probabilities. So notice when you flip a coin 3 times, you have a higher probability of getting 2 heads and the tails than you do of getting all heads, for instance. And that's because 2 appears 3 times in this, where 3 only appears once. And we'll be talking about that more now, and that idea really is a probability distribution, which is just looking at a certain random variable and seeing what probability is associated with each of those numbers in the random variable set. So now let's go ahead and take a look at that. Alright, so now we say a probability distribution of a random variable x is a function p of x, which assigns probabilities for each element in x. So basically we're going to be taking the probability of a certain number, and that number is going to be an element in the set of random variables x. And we'll actually see how we find those probabilities, but it's basically the way we found probabilities previously. It's just the number of things that correspond to that element divided by the number of things in the sample space. So we'll get to that in the example here. But there are some nice consequences of probability distributions, and they're basically consequences that we've seen for probabilities, and that's that, each probability is going to be a value in between 0 and 1, and if you add all the probabilities together, then you get 1 as a result. So here, x1, x2, and x3, all the way up to xn, are just all individual elements of x, so all of the possible elements in x. Now remember, x is a set of numbers specifically, so they're just each of those numbers. So in the previous example we had, x was 0, 1, 2, and 3, so now we can just jump right into this example. So this is from the previous example. X was, again, the numbers 0, 1, 2, and 3. Now specifically, if you look back, each of these values, 0, 1, 2, and 3, had a specific weight that went with it. Basically, how likely it is to occur in a random toss of 3 coins. So these would be the probabilities of those values. So how many times did 0 occur? 0 occurred actually only once. So out of the total outcomes that we listed out, there was only one of those 8 elements that actually had 0 heads. So the probability that corresponds to 0 is 1 over 8. Similarly, 1 and 2 each had 3 out of 8. And 3 had 1 out of 8. So there we go. These are the probabilities associated with each of these elements of the random variable x. And this is literally just the probability distribution. So very often when I think of probability distribution, I think of just this kind of table. Now there is a graph you can talk about, and the graph associated with the probability distribution is called a histogram. And a histogram is kind of like a bar graph, but it's very specific in the sense that we don't want spaces in between, and well, each of them have the same width, but I'll just show you specifically what it is here. So in this case, I want one spacing for each element in the random variables. So 0, 1, 2, and 3. And let's say this is 1. So let me see, this would be 1/2. This would be 1/4. That would be 1/8. And this would be 3/8 here. So this would represent 3 over 8. This would represent 1 over 8, just so I'm kind of to scale. So 0 and 3 both have this height here of 1/8. 1 and 2 both have 3/8 as their height. So notice why I said earlier it reminds you of a bar graph, because we have these bars associated with each of these numbers. And let me shade this now just so we can kind of see it in red, I guess. But this is the histogram of the probability distribution. So again, it's basically just what we would think of as the graph of the distribution, which is kind of nice. And there's different types of histograms too, as far as how you can categorize them. So you can categorize them as being skewed to the right, skewed to the left, or bell-shaped. In this case, this is a bell-shaped histogram. And to be quite honest, that topic gets a little more exaggerated as you go on in statistics. But for right now, this is just really basic intro. So that's all I'm going to say as far as histograms are concerned. And now we're going to talk a little more about probability distributions. I know I haven't done too many examples. In fact, this is only the same one example that we previously spoke about. But I think, honestly, this one example is okay because it gives us an idea as far as what they are. We'll see another example of distribution shortly, but that'll correspond to the next idea, which is expected value. So before we move on to the next example, we need to take a look at expected value in order for us to, I guess, generate, you can say, more interesting types of probability distributions. So let's take a look at expected value right now. Right, so let's say we have this given probability distribution, kind of like we saw previously, only instead of, I guess there were 4, instead of 4 entries, there's n entries, so x1, x2, x3, all the way to xn. And for the probabilities, let's label those as p1, p2, p3, all the way to pn. So n just represents the last labeling, I guess. So just a way to count how many you have. And then we can say that the expected value of the random variable x is given by this right here. So let me circle this in a different color just so we can put an emphasis on it, I guess. And yeah, it's e of x is the notation for expected value of the random variable x. And it's just literally multiplying all of the x values to the probabilities and then adding those results together. So that's what the expected value is defined to be. Now this idea, to be quite honest, has a few different applications. Expected value is what it sounds like. It's the expected value if you run the trial over and over again. So if you were to run the trial over and over infinitely many times, the value you expect to get at the end would be the expected value. So we'll do a few examples here so we can actually see what that means. But let me just say that expected value is also known as mean or average. That's literally what it is. In fact, if you were to add up all the values and divide by how many there are, it would be the same thing. And you will see that actually with this example. So of course, going back to the example we've been seeing all throughout this video, the tossing a coin 3 times example. So to find the expected value a little more simply, here's what we're going to do. We're going to create one more column, and the column is going to be the product of the previous two. So x times p of x. 0 times 1/8 is 0. 1 times 3/8 is 3/8. 2 times 3/8 is, I guess, 3/4, but I'll leave it at 6/8, just so we can add better because they have the same denominator. 3 times 1/8 is 3/8. So altogether what we get is the expected value is, well, it's all over 8, so let's see, it's going to be 0 plus 3 plus 6 plus 3 over 8. That's 12 over 8. 12 over 8 actually reduces to 3 over 2. And that's 1.5. So what this says is that if you were to run the experiment of flipping 3 coins, so imagine one trial, you flip a coin 3 times and you count your results, how many heads do you have at the end of that result? Let's say it's 2. Do it again, and let's say you get 2 again. So if you keep doing that and you write down your results, on average overall, you'll get 1.5. So that's basically what it is, the average of your results after running it a bunch of times. Now, obviously, it won't always be 1.5 because you can't actually run an experiment infinitely many times, but if you could, then this would be the result overall. And in fact, like I was saying, that if you were to actually write out the list we got previously, so if you remember, the list we got previously was the following. We had 1 0, we had 3 1s, we had 3 2s, and we had 1 3. So this was literally the list we had. If you remember, when we wrote our outcomes, were HH, HHT, and so on. So if you actually wrote them out, here I'm writing them in just order from smallest to greatest, you get this. Now if you add these together, it's no coincidence, you'll get 12. So notice these 3 add to 3, these 3, 2 3s add to 6, so that's 9 plus 3 is 12. And if you add these and divide by how many there are, which is 8, you indeed get all 12 over 8, which is 1.5. So it's kind of nice that expected value really just means mean or average, but it's it's just a different way of looking at it in the context of distributions anyways, probability distributions, that is. So now onto this example, all we need to do is create a third column here that's going to represent the product of the 2 previous columns. -1 times 1/2 is -1/2. 0 times 1/3 is 0. 1 times 1/6 is 1/6. Also, I'm not giving you any context as far as what this distribution represents. We can definitely check that it is indeed a distribution by adding the probabilities though. Notice each probability is less than 1 and bigger than 0, which is one of the results we had previously. Also, if it is indeed a probability distribution, this column should add to 1. All probabilities should add to 1. And if you add them, you get 1/2 plus 1/3 is 5/6. 5/6 plus 1/6 is indeed 1. So if you want to write the sum as being this row, for the probabilities, they'll always add to 1. So that's a way to kind of check to see if it is indeed a probability distribution. And here, this sum, well, that's just going to be our expected value. Now, in this case, we're going to get 1/6 minus 1/2. So just to do it on the board, 1/6 minus 1/2, let me write it like this. If you find a common denominator, multiplying this by 2 and multiplying this, I guess we could just multiply this by 3 actually. That was a little overboard. Yeah, just multiplying the second one by 3, top and bottom, we'll get 1 minus 3 over 6, which is -2 over 6. And of course, that reduces to -1/3. So here we get -1/3 as our expected value. So that's E of x. All right. Yeah, so this is our first instance of actually seeing a probability distribution that has negative x values, and what that kind of means is hard to interpret right now because the only one we have an understanding of is, well, representing number of things, and you can't have a negative number of something. So it means something else, basically. And in fact, we'll be taking a look at examples of that right now that will involve, well, essentially betting and gambling. So X would represent either winning a bet or losing a bet, and the actual amount would represent winning that amount or losing that amount. So in this case, in the context of gambling, this would represent, well, losing $1, breaking even, or gaining $1, something like that. So we'll take a look at an example where I'll actually write it out, and then we'll be able to hopefully translate it into a nice probability distribution and then find the expected value and go from there. Right, so finally something a little different from tossing a coin 3 times, now we're rolling the dice 3 times. Well, anyways, so on 3 rolls of a single die, you will lose $10 if a 5 turns up at least once, and you will win $7 otherwise. So now they're asking for what is the expected value of the game. So here what we have to do is we have to create basically a distribution, probability distribution. So X will represent the amount of money that we win or lose. If we win, it's positive. If we lose the amount, then it's negative. So we know either we will lose $10 or we will win $7. So let me write a plus just to indicate that. And the probability of, what is the probability of a 5 turning up at least once from a roll of 3 rolls of the die? Well, if you think about it, the probability of rolling a 5 once is, well, just 1 out of 6. But if you have 3 chances, then either you roll a 5 in one of the 3. So the probability of rolling a 5 on the first one, or a 5 on the second one, or a 5 on the third one is equal to the probability of rolling a 5 on each one of them, added together. So either we roll a 5 on the first, or on the second, or on the third. So here, all we're really doing is adding 1/6 to itself 3 times. And in fact, the same is true for any number because they all have equal probability. So it didn't have to be 5, it could have been, well, any number between 1 and 6, really. So of course, 1/6 plus 1/6 plus 1/6 is 3/6, which is 1/2. So that means the probability of this not occurring, believe it or not, is also 1/2. Sounds a little strange because it seems like we're rolling one number, and if you don't roll that one number, then, well, you would roll 5 other numbers. But this one number can have 3 chances to occur. So in total, it actually has a 50% chance of occurring overall, which is kind of funny when you think about it. So of course, how did I know this has to be 1/2? Because, well, first off, it says otherwise. So we know it has to be the complement of it. By complement, I just mean the amount that you need to add to 1, because remember, the sum for these probabilities is always 1. So if one's 1/2, the other one has to be 1/2 as well. And with that being said, we can just multiply these to get our next column. So that's -5 plus 7/2, which is 3.5, by the way. And then adding these together, we get -2.5. I guess -1.5. So the expected value E of x, in this case, is -1.5. And that is not really a good thing. So as it turns out, if you have a negative expected value, then, well, this basically means that the odds are against you to win. So if you go to any casino or any place that are holding some type of gambling event, chances are the game or whatever the event they're holding, we'll just call it a game, I guess, for simplicity, it will probably have a negative expected value because they want you to lose. It may be low, like here this is pretty high. Usually the expected value at casinos are like -17 cents or something like that. In that case, it's a pretty low expected value that's negative, but it's still negative, meaning that if you were to play the game a bunch of times, you're expected to lose. So just kind of keep that in mind. And if it's positive, then it's in favor for you to win. So in fact, fun fact here, if you think of counting cards in the game of blackjack, counting cards actually increases your chances of winning in the sense that it actually makes the expected value positive, in which case it would be worth it to play provided you know how to count cards, of course. Which, by the way, is banned. So I'm not promoting that at all. I'm just kind of stating the fun fact. Also, casinos try to regulate that in their own way nowadays anyways. Oh, also, an expected value of 0 means that the game is fair. So right now we're going to take a look at an example of a game where it's not completed for us and we want the game to be fair, so we have to figure out what the other result would have to be in order for the game to be fair. So let's take a look at that example right now. Right, so this is the last example that I was referring to earlier. Here a pair of dice is rolled once. Suppose you lose $10 if a 7 turns up and win $11 if 10 or 11 turns up. How much should you win or lose if any other number shows up in order for the game to be fair? So for us to actually figure out what's going on, well, notice there's going to be a total of 3 different values for x. There's going to be us losing $10, so negative 10, us winning $11, so that's 11, and the amount that we don't know, and they each have their corresponding, well, probabilities. So for p of x, we have to figure out what each probability is depending on the situation. So remember that when you roll a pair of dice, the possibility to roll in the 7 was the most. In fact, there are different ways of calculating these kinds of things. The way we did it was we considered rolling a 1, 2, 3, 4, 5, or 6 with one die, and then same thing with the other die. And then you can kind of see the different combinations that'll give you certain outcomes. So like here, this is a 2, this is a, I guess, 3, 4, 5, 6, 7. This would be a 3, 4, 5, 6, 7, is that right? Yeah, 6, 7, 8. This would be 4, 5, 6. So you kind of see there's a little bit of a pattern that I'm doing here. And 5, 6, 7, 8. So everything's kind of being shifted over. 9, and then this is 4, and 6 is 10. And then here, this is 6, 7, 8, 9, 10, 11. We kind of did this before. I don't know if I quite showed you like this, but this is a way to calculate how many ways you can roll certain numbers. And then finally, we have 11 and 12. So notice there's only one way to roll a 12, that's 2 6s. There's only one way to roll 2, that's 2 1s. And how many ways are there to roll a 7? Well, there's a total of 7 7s in this list, actually. Another way I wanted to show you that's kind of similar to this is if you wrote down the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the amount of ways you can roll these numbers with 2 dice, it's kind of a similar idea. But notice, 12, there's only one way to roll. 1, you can't roll a 1 with 2 pairs, with a pair of 2 dice. But there's one way of rolling a 2, and basically to get from 2 to 1, you add 1 to this number until you get to some number in the middle, and then you subtract back down. So this is 2, 3, 4, 5, 6. 7 is the highest, so that means you go back down. 5, 4, 3, 2, 1, because remember, lucky number 7, because of course it's not really luck, it's just that there's more ways of combining 7 from numbers 1 through 6 than any other number. Anyways, so this is another way of computing how many ways you can roll certain dice. So remember, negative 10 was losing $10. That's if a 7 turns up, the likelihood of a 7 turning up is 6 out of 36 total outcomes. And of course, 6 over 36 reduces to 1 over 6, but I'm going to leave it like this for purposes we'll see soon, hopefully. 11, if we win $11, either a 10 or an 11 roll up. Now remember, or should remind us of adding. So we're going to add the probabilities for 10 and 11. So here, 10 and 11. 3 ways you can roll a 10, 2 ways you can roll 11, so that's a total of 5 ways out of 36 possible combinations. And remember our insight for probabilities. In order for this to actually be a probability distribution, what must this column add to? The sum of this column must be 1. And you can kind of see, that's why I left it 36, and the denominator anyways. 6 plus 5 is 11, so it's 11 over 36. 11 over 36 plus what over 36 will be 1. Remember, 1 is 36 over 36. So really we need to find out What number can you add 11 to make 36? That's of course 36 minus 11, which is 25. So it's 25 out of 36 ways of rolling any other number besides 10, 11, or 7, basically. Now we want to figure out what this number is in order for the game to be fair. Now remember, a fair game means its expectation value is 0. So what the word fair in this context means is that e of x is equal to 0. So this is our unknown. We could call it x, I guess. That's fine. I'll call it x. That's our unknown. We're going to solve for this x by, well, first trying to compute the expectation, the expected value that is, by multiplying these numbers together. We want the result to add to 0, and then we're going to solve for x. So I'm going to clean this up, and then we'll write that out right now. So here I have things cleaned up. Now remember, for expectation, or expected value, we're multiplying these two columns together. So we're getting the x times p of x column. Negative 10 times, let's just leave it with the denominator 36. That's negative 60 over 36. 5 times 11 is 55 over 36. And this is, well, 25x over 36. And we want the sum to be 0. And here I think it's kind of easy to see. So the equation we end up getting is this. Negative 60 over 36 plus 55 over 36 plus 25x over 36 is equal to 0. Of course, multiplying both sides by 36, just like that, we'll clear the denominators. 36 times 0 is still 0 on the right side. The non-x's combine in this case to negative 5. So we get negative 5 plus 25x is equal to 0. Good. So now what we need to do is just add 5 to the other side. Divide by 25. And this, of course, reduces to 1 over 5, which is 20 cents. So you'd have to win 20 cents. And I know win because it's positive 20. So must win. Let me say 20 cents in order for the game to be fair. Order for a game to be fair. There we go. Awesome. So again, that's all I wanted to say for 8.5. I know we saw a pretty decent amount of examples in this section, to be quite honest. The ideas were pretty simple, I want to say. Really, I just showed you, again, these three things, and I guess beyond that, we spoke a little bit about histograms, a little bit about fairness. And that's really it. In fact, that basically concludes the whole class. This is the last section in the class for finite math. So I really hope you enjoyed, what we saw in this class. I really hope you enjoyed the way I've been explaining things and the way I've been dealing with the whole situation. Well, anyways, I really hope you enjoyed this. I know I enjoyed it, like I always do. I'll see you in the next videos for the reviews. See you then.